We also have another case in oblique triangles. It's called the ambiguous case. It's where we have a known side, and then the angle. Now, the reason why it's ambiguous is because it can determine four different types of possible shapes. So I need you to use your imagination here. So imagine I have some side that I know, some other side, and an angle. So what can you imagine then if this side is already determined and that side's lengths are already determined? Doesn't it depend on a couple of factors? What if the angle of A was very large? If that was the case, then this line would start to move on up and make this line farther and farther away. And no triangle would be formed at all. Okay, now imagine if we did it the other way. What if we started to decrease the angle? What happens to these two legs? Well, those two legs, sooner or later, this line is going to touch down here as this angle gets smaller. And then we have what we call a triangle or a one triangle. If this length, A, was the exact same length as the altitude of that triangle, then as it came on down, it would start to slide right into a right triangle position. And in that particular case, we would have one triangle formed, but it'd be a right triangle. Then lastly, if this side of A, as A comes down, as the angle gets smaller, but A itself is greater than the altitude, then we would get a situation, there would be two triangles. Because this length then, as it comes down, it would form one triangle there, but it would also form another triangle right there, assuming that A is less than B. So that's what we call the ambiguous case of side-side angle. When we know just those three things, we do not know which of the four positions we'll have. We'll either have one oblique triangle, we'll have one right triangle, or we'll have two oblique triangles formed by those three sides, or we will not have a triangle formed at all. And all of that depends on the relationship or the height of H. And H, as we discovered earlier from the law of sines, is formed by B times the sine of A. So that's what we need to understand first. What is the relationship, or what is the height, and what is its relationship to the other sides? As we work on that, we can start to figure out if this triangle, an SSA triangle, can be solved. So let's look at one case. Now I already drew a sketch, but I don't know if this sketch is accurate. But it's the best I can do with the given information where I know an angle, a side, and a side, or side-side angle. Let's begin looking at what we can discover. I already have a relationship established, or ratio of A to its side. So I know that I can use the law of sines with that particular part in place. So I will do A over the sine of A. I have B defined. I know B, so I'm going to use B. So I have B over the sine of B. Out of all three of those, or out of all four of those, I know three of them. The one I do not know is the sine of B. So let's solve that for the sine of B. All right, just understood my proportions, solve that for the sine of B. The values I know then, B is 62. Sine of A is sine of 43. All over A, which is an 81. So my sine of B, once I calculate all that out, oops, typing the wrong one again, 62 times sine 43 divided by 81 equals 0.5220, blah, blah, blah. So I'm going to round off to 4 decimal points there. So the sine of B is 0.5220, so I'll take the inverse sine. of that solution. To figure out what B is, and B is 31.46, 31.5. 31.5 degrees. All right, for that to be the case then, I know then the sine, there's two places that the sine of B is 0.5220. If you remember that, the first one is at 30 or at 5.220 or 31.5 degrees. The other one is at where sine is positive, is 180 degrees minus that 31.5, and that equals 148.5. So the sine of B equaling 0.5220, where B equals 31.5 degrees, produces two values of sine. B is positive, so I know one's in the first and second quadrant. The reason why it's ambiguous is I get two values here. So can those two values work? Well, 31.5 degrees is a possibility. If I have 148.5 in there, well, 148.5 plus 43 degrees is already more than 180 degrees. So I know that 148.5 cannot be one of the degree measurements. Therefore, I have to have the angle being 31.5 degrees. From there, we can check the rest of the triangles, and it's just a matter of just plugging in things that we don't have. 43 plus 31 plus C equals 180. That's 74.5 plus C equals 180. C equals 105.5. Did I do that correct, folks? 105.5. Now I have all the interior angles. I have one side remaining. And so I can just again use the application again. So we already knew B. So let's do C over the sine of C. Oh, sorry, we already knew A. So let's do A over the sine of A. Solve that for what I don't know, which is C. So C equals A times the sine of C all over the sine of A. A is 81. Sine of C, which is 105.5. All over sine of A, which is 43. And I'm curious, just like you guys are, 81 times the sine of 105.5 divided by the sine of 43 equals 114.45. 114.45. And that gives me the value right here. And that makes reasonable sense. Since C is the largest angle, that should extend to the largest side. 31.5 is the smallest angle, that should extend to the shortest side. And so therefore, we were able to solve this ambiguous case by identifying it being the situation where we have one triangle formed.